Today's speaker is Aaron Kettner from here, and we'll talk about topological graphs and C-star correspondences.
Thank you. That's indeed what I want to do. And I will start with telling you what topological graphs are. Okay, so maybe the more familiar thing are discrete graphs. Okay, what's a discrete graph? I guess the immediate picture that everybody has in mind is of some vertices and arrows between them and so on. But formally, we can express it as having two discrete sets. Which are the vertex space and the edge space, or set of all vertices, set of all edges, and then range and source maps, which tell us how these edges are between the vertices. So R and S are maps from E1 to E0, and these are the range and the source. And now we could, in principle, just ask E0 and E1 to be topological spaces instead of discrete sets, and these these range and source maps to be continuous maps. So a compact topological graph this was defined by Katsura in 2003. Consists of compact Hausdorff spaces E0 and E1, which again we call the vertex and the edge space, and two maps, S from E1 to E0, and R from E1 to E0, where S should be a covering map, and R should be continuous. So as a remark, I will only talk about compact topological graphs. Of course, you can define this more generally. And then you would want S not to be a covering map, but to be a local homomorphism. So if anybody has seen this definition before, you almost certainly saw that S is required to be a local homeomorphism. For compact spaces, a local homomorphism is automatically a covering map. Right, so covering map means that each point in this case in E0 has an open neighborhood, and also there exists some natural number such that S inverse of U is homomorphic to the disjoint union of n copies of U in such a way that this diagram commutes. So you want this to preserve the base space. Okay, so here the map is S, and here the map is the sort of obvious projection down onto U. Right, so the picture is you have a circle, for example, take a circle and then take the two-sheeted covering that is given by taking the circle and kind of wrapping it around. And then you can project down.
But you want this one n forever.
Yeah, that's a good point. So in the pre-seminar, I asked that there's one n which is fixed for each point. In general, you don't have to ask that. I mean, it's going to be fixed on connected components of the space, certainly. So yeah, doesn't really, I mean, for the purposes of this talk, we can always assume the n to be fixed. Yeah, thank you. That's good. Okay, so so why do we do this? What's the point of topological graphs, right? The point is that you can build C-star algebras from them. So from a discrete graph, you can build its graph C-star algebra. We've seen this in the Mali seminar a few weeks ago. And from a topological graph, you can first form a C-star correspondence and then you can form its Conspimson algebra. I did not say this in the pre-seminar, but for each C-star correspondence, there's a canonical way to form a C-star algebra, which is called the Conspimson algebra. Okay, and this diagram commutes, right? So every discrete graph is in particular a topological graph. The definition I've given above for compact graphs, of course, you need a finite graph. You need edge and vertex space to be finite. And then if you sort of go this way, right? If you regard a discrete graph as a topological graph, form the C-star correspondence, and form the Conspimson algebra, you get exactly the graph C-star algebra. So that's the reason why Katsura introduced these topological graphs as a way to obtain interesting C-star algebras. Okay, and indeed, this is a very broad class of C-star algebras. You can obtain these this way. For example, you can get all Kirchberg algebras, which are important in the classification program. You can get cross products by the integers of commutative C-star algebras. So this is a very important class of C-star algebras.
Did Katsura show all of that? Could you get these various C-star algebras?
Yes. So he has the series of papers developing this theory. And in the final one, he constructs all Kirchberg algebras from topological graphs. Yeah.
Anyway, higher graphs.
You mean higher rank topological, like define higher rank topological graphs or something like this? Interesting.
Higher rank graphs.
No, they are something a bit more general. So for a higher rank graph, yeah, it is related. It's not the same thing, though. Yeah.
The idea is a discrete graph, higher graph. You extend it again, and you have a line here. I'm trying to make it into a square.
Like coming out of the blackboard. Go to the okay.
Then you would put their higher rank graphs.
Yeah.
And put out just a higher rank of that. And then you have on the other side graphs these folks, Spencer, higher rank graph, and then higher rank.
Yeah, exactly. And it is, I mean, for higher rank graphs, you do get some related construction. So instead of one C-star correspondence, you'd have a family of C-star correspondences. And then from that. Yeah. Thanks. Okay, so now I want to show you this first step, how to get from a topological graph or a compact topological graph to a C-star correspondence. And in fact, the people who attended the pre-seminar have already seen this, okay? Because we already constructed a C-star correspondence from a covering map and a continuous map R. So I will recall this construction. Let E0 R and S be a compact topological graph. Well, then C of E1 is a right C of E0 module, where the multiplication is given by the following. you take a function g in continuous functions on E1. You multiply from the right a continuous function on E0. You evaluate the whole thing in some point y of E1. Okay, so y is in E1. What is this? This is g of y f of s of y. Okay, gives you the module structure. Then complete, well, you don't need to complete. Then you form you get a C of E naught valued in a product. Again, in this way, so x in this case is in E naught, right? This whole thing should be a continuous function on E naught. So if we plug in x in E naught, then we look at its fiber, S inverse of x, and then you sum over the values of the function over the points of this fiber. Sorry, again? Right, so this sum is finite because we are talking about a covering map, and both these spaces are compact. So this will be a finite set, S inverse of x. It's a finite set. And then sure, you have to show that this defines indeed a continuous function, right? But you can show this. So this gives us C if we not valued in a product, and we obtain a Hilbert C of E naught module, which we denote by gamma of S. And now we want to build a left action. This will take a function f in C of E naught. We apply it to a function g in C of E1, evaluate it in y, and we get f of r of y. And this turns gamma of s into a C-star correspondence I over C of E naught. And we will write gamma of E for the C-star correspondence. Okay. So this is how you use this range map. Yeah, right. So notice this maybe topological graph. We have these two maps, S and R, and we use S to build the right module structure and the inner product, and we use R to build the left multiplication. And this is also why we have to ask S to be a covering map or to be a local homeomorphism, and R can just be continuous, because on the right we want this inner product and we want it to be finitely generated effective. Okay. Oh yeah, I should have said this here, I'm sorry. So the Hilbert module will be finitely generated projective. Which means that we have some vector bundle associated to it. Okay. And now as a remark, there is a slightly more general construction of twisted topological graphs. What is a twisted topological graph? It is a usual topological graph. Let's say E. Plus a line bundle, a complex line bundle. L over the edge space. A complex line bundle is just a complex vector bundle where the fibers are one-dimensional. Okay, so yeah, just a complex vector bundle, all of whose fibers are isomorphic to C. Right, so this is what one would call a twisted topological graph, a topological graph plus a complex line bundle. So think of this picture here. Think of our covering of the circle, twofold covering. Now you just have a line bundle over this covering space. And that would be your twisted topological graph. And you can again, sorry? Between the line bundle and the... Yeah, exactly. So there's no, yeah. It's just a line bundle on this edge space. And now you can again construct a C-star correspondence. And we construct it in exactly the same way as before. Just that instead of taking continuous functions on the edge space, we take continuous sections of the line bundle. And we again obtain a C-star correspondence, which we call gamma of EL. Okay, so everywhere here, if you think about it, you can swap C of E1 with the continuous sections of this line bundle. You still have this this multiplication. You can still define the inner product, and you obtain a C-star correspondence. I will try to avoid twists as much as possible, but there are some parts where I cannot avoid them, so I needed to at least mention them.
What's it called?
Oh, because you would think of this line bundle as a twist. So it's twisting the structure somehow. Yes. So for these, if you have a C-star algebra associated to a twisted topological graph, you get a twisted group. Exactly, yeah. You would build the underlying groupoid from the topological graph and the twist over it from the line bundle, yeah. Yeah, an untwisted groupoid. Yeah. Exactly. So now we come to the question which I want to address, which is the following. If you are given a C-star correspondence, E over the commutative C-star algebra C of X, does there exist a twisted, maybe, topological graph whose vertex space should be X? such that the C-star correspondence built from this topological graph is exactly the C-star correspondence you started with. So that's the question I want to address. Okay, you might wonder, why is this interesting? Okay, why do we care? If we meet a C-star correspondence in the wild, why do we care whether it's induced by a topological graph? And the answer is that topological graphs are comparatively nice. So as Marzi pointed out, there's a twisted groupoid. So if you consider the C-star algebra associated to a twisted topological graph, there's a twisted groupoid associated to it. There's results relating the structure of the C-star algebra to the structure of the topological graph. For example, you can say stuff about simplicity, about the ideal structure of the C-star algebra, about pure infiniteness, about traces, about KMS states. Okay, there's quite a lot of stuff you can do if you know that your C-star algebra comes from a topological graph. So it's useful to know, okay, if I'm given a C-star correspondence, okay, quite often I know that my C-star algebra comes from a C-star correspondence. Can I find a twisted topological graph inducing it so that I have access to all these results? And there's one theorem in this direction which I want to mention. This is from 2023 from Rodrigo Pausino, Abraham and Aidan Sims. If X is a second countable compact Hausdorff space, and E a Hilbert CFX module, then the following are equivalent. I'm going to slightly rephrase their statement in the language that we've been using in this talk. So first of all, this Hilbert module is isomorphic to gamma of S. For some covering. So gamma of S is this Hilbert module we constructed from a covering above. And the second point is E is isomorphic to continuous sections of some vector bundle. And this vector bundle has an atlas whose transition functions take values in the permutation matrices. Okay, so this is how we can recognize those Hilbert modules which come from coverings, which basically means they come from topological graphs. Forgetting about the range map and the left action. It's exactly those where the vector bundle has an atlas such that the transition functions are permutation matrices. Okay. Now comes the main result of this talk, generalizing this. Let E, or let's write E phi, be a C-star correspondence. Over C of X. And okay, I'm just going to ask it to be finitely generated projective to have access to this vector bundle picture. take the vector bundle associated to it, such that continuous sections are isomorphic to E as a right Hilbert CFX module. Then there are bijective correspondences between isomorphism classes of the following objects. Okay, so first of all, twisted or compact twisted topological graphs EL, where E is, I always write E for this topological graph consisting of vertex space, edge space, range, and source, such that E is the C-star correspondence associated to this twisted topological graph. Okay, so this is the thing that I'm actually interested in. I'm interested in topological graphs inducing my C-star correspondence. Okay, and this tells me that these are in one-to-one correspondence to the following things. There's going to be two more. So, secondly, maximal abelian subalgebras. In the adjoint bilinear operators of E, which contain the image of the left action, such that the image of phi is contained in D. And the third thing is a condition similar to this, where was it? Oh, it's right there. Condition similar to this with the transition functions. So, and here I'm going to use some words which I have to explain in a second. Atlases of V whose transition functions take values in some group, which I'm going to explain in a second. So it's the unitary group of the normalizers of the canonical diagonal in the matrices, n times n matrices. And these atlases should diagonalize the left action, which is another word I have to explain, phrase I have to explain. Nice. Right. So this is how you can recognize C-star correspondences which come from twisted topological graphs, either by looking at certain maximal abelian subalgebras in these adjoint bilinear operators, or by looking at atlases of the vector bundle, which is associated to the correspondence. And I can draw a triangle like this. So here we have twisted topological graphs. Then there's a one-to-one correspondence to atlases with these special transition functions. And then there's a one-to-one correspondence again to certain subalgebras of these adjoint bilinear operators. Okay, all of these are one-to-one correspondences and they preserve isomorphism classes. So if you define your notion of isomorphism the right way. Okay, so I should explain what this stuff means, but first I need to clean the board. Uh-huh.
Since you wrote this for objects, so do you know what's happening on morphisms? So is this functorial or?
Yeah, so it depends on what morphisms you choose, I guess. So I mean, I think the answer would be yes, but I haven't looked at it except for looking at isomorphisms, right? So if you have an isomorphism between two such objects, you get an isomorphism here and so on. But I haven't looked at more general morphisms, but it will certainly also be fine. Okay, so what do these phrases mean in the third point for these atlases? Okay, so regarding 3. Take an atlas of your vector bundle, which we again write as a triple EXP, and HI is that's a chart. Okay, and recall the definition of transition functions. Recall that we had these continuous functions, Gij, from the intersection of Ui and Uj into the general linear group, JLNC, such that Hi inverse composed with Hj of xv is equal to x Gij of x applied to v. Okay, and so these are the transition functions that I'm talking about. Now we fix orthonormal basis of C to the n. Okay, and then Dn is supposed to be the subalgebra of diagonal matrices. With respect to this choice of orthonormal basis. Okay, and then this group, it's the unitary group of the normalizers of the subalgebra. This consists of all unitary matrices such that U star Dn, U is contained in Dn. Okay, so I'm asking, if I conjugate by this unitary, then I preserve diagonal matrices. Okay, so why this notation? If I allow U to be any matrix, then I would call matrices which fulfill this. I would say that they normalize this diagonal, and you would write n dn, so it's the normalizers of this diagonal, and then it's the unitary group of the normalizers. And how does this look like explicitly? If you think about it, what we want is matrices such that U star, some diagonal matrix times U is again the diagonal. So all we're allowed to do is to permute the diagonal entries and to multiply them with some numbers. Okay, so this will be exactly the set of matrices of the form sigma times lambda, where sigma is a permutation matrix. So I identify Sn with the corresponding permutation matrices, and lambda is a unitary diagonal matrix. Okay, it's in the unitary group of this diagonal. So these guys are like almost permutation matrices, except that instead of ones, we can put some complex numbers of modulus 1. But they're almost permutation matrices. Okay, so that makes the connection to this previous theorem of Frausino and Sims. If you have a topological graph, and using your correspondence, you get permutation matrices. If you have a twisted topological graph, you need to somehow encode that line bundle, and this line bundle will be encoded in these in this unitary diagonal matrix. Yeah, actually, there's part of the theorem which I forgot. Sorry. Because the twist is trivial if and only if you actually land in the permutation matrices. Okay, so we recover this previous theorem. So the twist L is trivial if and only if the atlas has permutation matrix valued transition functions. Okay. Right, and there was one more thing. So now we know how our transition functions should look like. They should almost be permutation matrices up to some complex numbers of modulus 1. Now there was this other thing of the atlas diagonalizing the left action. What does that mean? So the atlas diagonalizes the left action. If, okay, for all I and for all k from 1 to n, and for all f in C of x, or not x, oh yes, x, that's x. F in C of x, I want this guy, hi x ek, to be an eigenvector of phi of f, so the left action, acting in this fiber. Okay, so hi was my chart, ek was the canonical basis vector, kth canonical basis vector. So we take this canonical basis vector, we push it into the vector bundle using the chart, and then that should be an eigenvector of this left action, phi of f, acting in this fiber. Okay, so this tells us that the atlas has to be compatible with the left action in a certain way. Okay, so if we only cared about the Hilbert module, we didn't care about the left action, we could forget this condition, but somehow we need our atlas to be compatible with this left action to get a topological graph. And this compatibility is expressed by exactly this, the left action being diagonalized by these special vectors. Okay. Up. Now in the last 10 to 15 minutes, I want to sketch the proof. Because actually the construction itself is probably the interesting bit. Or at least in applications would be the interesting bit. Okay, let me number the arrows in this diagram. So this is 1, this is 2, and this is 3. Okay, and I don't want to do all of the constructions. I mean, what you have to do is you have to go back and forth in each direction. So that's like six directions. Then you need to show that these things are inverse to each other and that it respects isomorphism classes. But what I want to do is at least go around the diagram once. So start with a maximal abelian subalgebra, construct the twisted topological graph, then construct the atlas, and then go back to the subalgebra. So let's look at one in this diagram. Take a maximal abelian subalgebra, which contains the image of the left action. Okay, so what do we do? How do we get a topological graph? First of all, we can regard, so right multiplication by functions in C of x, you can regard those as operators acting on E. Okay, so define an operator M of f simply by saying, okay, M of f applied to xi should just be right multiplication with f. Okay, this is going to define you an adjointable linear C of x linear operator. Note that the image of this map, okay, so yeah, the image of this map is contained in the center of L of E, because by definition elements of L of E are C of x linear. So of course they commute with any such operator by definition. So this is supposed to be the center of L of E, which implies that this image is contained in D, in our massa, because it's maximal abelian. So if I commute with everything, I in particular commute with everything in D, which means that I need to be contained in D. Okay, and now this means we can regard M as a map from C of x into D, because its image lands in D. We again write M for this map, and the same holds for the left action. Because by assumption, the image of the left action is contained in D. Okay, and by abuse of notation, we write M and phi again. Now you take the Gelfand duals. M hat, which now goes from the Gelfand spectrum of D to X, and phi hat, which does the same. Okay. Now recall that if we build a module or a C-star correspondence from a topological graph, we use the source map to encode right multiplication and the range map to build the left action. So here it should be, well, sort of the other way around, right? From the left action, we should get the range map, and from the right multiplication, we should get the source map, which is exactly what happens. So then you can show that that M hat is a covering map. And we obtain a topological graph E0, E1, R and S, where E0 is X, E1 is the Gelfand spectrum of D. The range map is the Gelfand dual of phi, and the source map is the Gelfand dual of M. This defines a topological graph. And Now, how do we get the twist? This is just a topological graph. In general, you will have to consider a twist. We consider E as a D module, which we can do for E as a D module, right? Because the thing that we want to construct is a line bundle over the edge space, meaning a line bundle over D hat. So this would correspond to a module over D. So it's exactly this. So you just regard E as a D module, which we can do. I mean, multiplication by elements of D is just applying the operator, right? D is a subset of the joint bilinear operators on E. And then show that this is finitely generated projective. And its fibers are one-dimensional. And so we obtain that ED is given by continuous sections of a complex line bundle. Over D hat. And then you need to show that you indeed recover the C-star correspondence you started with from this twisted topology. Okay. So that's going from this maximal abelian subalgebra to the twisted topological graph. Now let's go from the twisted topological graph to the atlas. What's the time? Let E be a compact topological graph. And for this direction, I want to ignore the twist. Okay. Yeah, I know it doesn't add that much. It just makes it a bit more complicated. Okay, such that the C-star correspondence associated to this topological graph is exactly the C-star correspondence we started with. If we are given this, what do we do? The source map is a covering, and we will assume it's an n-sheeted covering, so this the cardinality of the fibers is constant. And there's a one-to-one correspondence between n-sheeted coverings over a space and principal Sn bundles, where Sn is the permutation group. Okay, so a principal bundle, as Thomas mentioned before, is yeah, it's sort of like a vector bundle where in the fibers you have groups, right? So each group is each fiber is given by a group. Yeah, and so you take this principal bundles. So let's say we take a principal Sn bundle P, which encodes our covering. So okay, maybe I should quickly say how this works. So if you have your covering, you can like choose sets in the base space. You can choose an open cover of the base space over which the covering is trivial, right? And then you look at how these copies of your set in the base space, how they are like swapped. So I think you would call this the monodromy action, something like this. The way back, you use the associated bundle construction. So you, of course, have an action of Sn on the space, on the set with n elements. And then you can take the associated bundle under this action. Take the associated bundle under this action, and then the bundle projection of this fiber bundle will be your covering map. Okay. So you take this principal bundle and you show that the Hilbert module you're looking at is isomorphic to continuous sections of the associated vector bundle. Okay, so this is S Hilbert CFX modules. Where this guy is the associated bundle with respect to the representation of the permutation group on C to the n by permutation matrices. Okay, so this is a vector bundle. You can take continuous sections, and as a Hilbert CFX module, this is the same thing as what you started with. And now this means that the vector bundle that we are looking at, the vector bundle corresponding to this module, is isomorphic to exactly this associated bundle. Because of SES1, because this is unique up to isomorphism. And this tells you that, well, an atlas of P as a principal bundle, you take an atlas of P as a principal bundle, you obtain an atlas of your vector bundle. This will induce an atlas of the associated bundle, and then it induces an atlas of V. And because this atlas comes from the principal N bundle, its transition functions will be permutation matrices. Okay, so this is how you get your atlas, which has the nice transition functions you want. And then you need to show that this atlas diagonalizes the left action. Okay. And now if you have a twist, if we start with a twist, then instead of an SN bundle, you get a principal bundle over with a structure group, this unitary group of the normalizers of Dn. And then you can do a similar construction to get an atlas of the vector bundle. Okay, so this is how you get from the graph to the atlas. Now, very quickly, the last thing: how do I get from the atlas to this subalgebra? Take an atlas of your vector bundle. Okay, with the right transition functions. Now I again have to. Yeah, okay, I'll just clean before I start this. Take an atlas with the right transition functions, Now, what is always true is that if E is finitely generate projective Hilbert module over C of X with a constant dimension of fibers, which I'm assuming, then it's a fiber bundle. Okay, so M is a principal principal bundle whose structure group are the automorphisms of n times n matrices. Okay, so we can always write the C-star algebra as a fiber bundle whose fibers are matrices. And then from this atlas of V, we obtain atlas of M with transition functions not in this group, but in a subgroup. Okay, so this is maybe, I'm going to tell you what this group is in a second, but if we have an atlas of a vector bundle, so we can trivialize it locally, then it makes sense that also the operators on the sections of this vector bundle should be trivialized, should just be a product of continuous functions on the base space with matrices. Okay, so if we choose an atlas of the vector bundle, we obtain an atlas of this guy. And what is this group? Automorphisms of M, N, which preserve the diagonal. These are, well, they're exactly what I just said. So they're all automorphisms of Mn such that phi of dn is equal to dn. Okay. Now, all automorphisms of Mn are inner, so they're implemented by unitaries. Okay, so this guy is nothing but all of those automorphisms which are induced by unitaries. So okay, can I write this? I mean the automorphism of Mn that sends a matrix to U star AU. All of those automorphisms of Mn which are implemented by unitaries in our group that we considered. Okay. And that's why an atlas, if the transition functions of this atlas are in here, then the transition functions of the induced atlas will lie in this group. And now the last line is that this implies, by a result of Xin Li and Jean Reno from 2019, that L of E has a Cartan subalgebra. In particular, a maximal abelian subalgebra. I should not. I haven't introduced what Cartans are, so I'm just going to say maximal abelian subalgebra. And then you need to show all this D. Show that this indeed contains the image of the left. Oh, okay, I'm already over time. Sorry. Yeah, that's it.
Thanks for everything. Do we have any questions in the audience? Question?
Yes. Up to you.
You mentioned that once you have this theorem, and so you have a C-star correspondence, and now you know that it comes from a topological graph that this tells you something about its structure.
Of the conspicuous algebra.
Yeah. So what could you remind me, like what sort of things, what sort of consequences does this have as far as structural results go for?
for the Kuhn-Pimsner algebra. So first of all, you get a twisted groupoid,
Right.
which is always nice. And then, I mean, there's a lot of things you can do with this groupoid. So
Okay.
just for that, it would be nice to know. But also there is some work of Katsura on, so for example, there's a notion of minimality for graphs and also for topological graphs, right? And there's also a notion of freeness. So you can look at orbits of points under, going along edges. And you can define minimality and freeness of graphs. And then I think a topological, the Kuhn-Pimsner algebra of a topological graph is simple if and only if the topological graph is minimal and topologically free or something like this.
Okay. So.
Hmm?
Okay.
Yeah, exactly. So it's exactly like correspondences.
Okay. Thanks.
Another thing would be pure infiniteness. Can characterize pure infiniteness in terms of the graph. Yeah. There's this property called contracting. So as far as I know, there's no if and only if condition, but you can say if the graph has this property called that it's contracting, whatever that means, then the Kuhn-Pimsner algebra is purely infinite.
Is it possible perhaps to go beyond the commutative case where it's C of X?
That's an excellent question. And yes, I mean, so for non-commutative C-star algebras, there's this framework of groupoids and groupoid correspondences. And that's what you would have to use. So instead of taking C of X, you would take a groupoid C-star algebra, maybe a twisted groupoid C-star algebra. And then instead of your topological graph, you would look at groupoid correspondences. And then I'm not sure, then you can at least ask for this guy, right? So this would be, you would ask for a Catan subalgebra in the C-star algebra. And for this, I'm not so sure. This, I was thinking maybe one could do something with, these non-commutative principal bundles. But I really don't know.
On point 3, you look at addresses of your vector bundle, but you could more generally consider collection of transition functions which satisfy these co-cycle conditions, so that you define a vector bundle. Could you build replacements of 1 and 2 such that their correspondences to this more general?
Wait, but in this you start with the C-star correspondence. So you start like the vector bundle is given to you, right? So
my question is if you put in 3, can extend this condition to more general transition functions, not starting with a vector bundle, but
okay, so saying, okay, if I have a system of transition functions, well, then you could build the vector bundle, you could build the Hilbert module. You would somehow have to get a left action. So I guess this is not given, not included. Right, but then I think you should be, I mean, then I think it should follow that that all of this works in the same way. I mean, so in what sense is this more general? Because if I have the system of transition functions, I can build a vector bundle, right? So I get back into this setting somehow.
But here, you only see one vector bundle. Maybe there's a more there are correspondences between bigger sets.
Oh, not fixing the vector bundle, but somehow.
But on those bigger sets, you put a Williams relation which distinguish between vector bundles.
Aha, okay, I see. Okay. I get it now. But I don't know.
Okay.
Thanks.
Yeah, I ask you. So, just kind of following up what Ray was about extending this. What about, okay, leave commutativity alone, but getting rid of the family generated? Yeah.
Yeah, I mean, I would think that something similar should be true, but it just the methods of proving it would have to be very different because I use this sort of like principal bundle, associated bundle picture a lot and the vector bundle. So, then you would get bundles which are not locally trivial.
I was thinking of what I had in mind was finally generated, countably generated. So then you're in like concentric group.
Okay.
Just wondering, developing this in the language of concentric. I don't know what, I don't have nothing in mind.
Oh, so then you would get like bundles whose fibers are Hilbert spaces.
I guess.
Like infinite or infinite vector spaces. Yeah. Infinite dimensional vector spaces. Would they be allowed to still be locally trivial for this Kunz semigroup picture? Is that in any way relevant?
I don't, but I just mean in general for a secret algebra, you look at projected A models, but can't be generated Hilbert's A models. This is just another picture of the person.
Right. Right. I don't know. I don't know. Yeah.
I don't know.
Maybe a so here in the theorem you start with this vector bundle and then somehow in the proof you show on this left blackboard here. So does this say that this is globally trivial or did it is some local detection?
Oh, you mean this? Sorry, this is a bit stupid from me. What I mean is when I write this, I might mean the associated bundle with respect to some action. So let's say I should do this differently. So okay, let's say we write, I don't know, pi for the representation of Sn on matrices, bounded linear operators on C to the n. Then this would be the associated bundle of this principal bundle with respect to this representation. So, yeah.
Wondering between all of the vector bundles that you start with have to be
no, yeah, exactly. That's an interesting question, though. If you take a non-trivial twist, then you can certainly get non-trivial vector bundles. But in this paper of Frosino and Sims, they ask if you just take a topological graph without a twist, can you get a non-trivial vector bundle? Okay, so equivalently, now in this language, this would mean if I take a principal Sn bundle, can I find such a bundle such that the associated vector bundle is non-trivial? So they left this open, and last week or 2 weeks ago, I asked ChatGPT this exact question, and it came up with something. So it seems like the answer is yes. You can you can get non-trivial vector bundles.
Because maybe this might also give some indication to the quantum setting, let's say, because the globally trivial ones, this would be the smash product algebras, and that if you have this up to some twist, and this is the cross product algebras, so things, I don't know, could correspond to some cleaving maps or
okay, I'd like to hear more about this. I'm not sure if I understand all the words at this
I'm also not sure, but yeah.
Cool.
Any further questions, Petter?
No. So the category of C-star algebras with star homomorphisms is not a bit.
If you say this, if you change the topology, right? So, say for example, if you have some topology on your space, and then change the topology for discrete one and take the identity map. So are you able to describe the canonical kind of?
I'm not sure if I understand the question. Is that about C? No. You take a topological space and then you.
So you keep the topology you had at the beginning. You have some topology on it.
on the space X, the base space. Uh-huh.
Then you change, then you take another situation and take discrete topology.
Uh-huh.
So the question, if you take the identity map, what is the kernel and concurrent such morphism in the topological system? Or it would be interesting.
Or when you say topological C-star algebras, do you mean C-star, like continuous fields of C-star algebras? Or what kind of?
Map, topological system algebra, whatever.
Wait, but the word topological C-star algebra, do you mean
Yeah, topological.
sorry, yeah. Uh-huh.
I don't know, graph or graph topological, I don't know.
Okay, so so you sort of transition into the back into the discrete picture, and you I don't know. Sorry. Simple answers. I don't know.
In general, these masses are, well, they're cartans. Do you know if they're?
They're always.
They're
yeah.
always
I could
cartans.
have replaced
Okay.
the word
Okay.
massa with the word Catan. So this is so this paper by Lee and Renaud, which I cited there. What they do is they study Catan subalgebras in homogeneous C-star algebras, and every n homogeneous C-star algebra is of this form. It's an associated bundle. So you have some principal bundle like this in the background, and then you take the associated bundle. And yeah, then they study Catan subalgebras of such guys, and then it's automatically, as long as it's a massa, it's always a Catan.
Any other questions? If not, let's thank Aaron for the very nice talk. Do we have a speaker? Oh, there will be two speakers. A double header. Leo Sean McCormick and Francisco Manuel Castella Simawa, both from Queen Mary University. So hope to see you there.